To understand the deviations in the from the periodic trends for electron affinity and ionization energy, we're going to have to look at how electrons interact with other electrons. And we're going to consider nitrogen first. Nitrogen is 1s2, 2s2, 2p3. And so here it is, E equals 0, 2p, 2s, and 1s. The first 4 electrons are clear. The 5th electron is in there in the 2p. And now the next 2p electron, and now we're going to start considering the interaction of electrons to electrons. It could either go to the orbital where there is an electron already, or it could go to an orbital where there's no electron. And electrons which go to the same orbital are actually closer together, and electrons repel. And so therefore the electron is lower in energy when it goes to a different orbital, a different atomic orbital. And they go to the different atomic orbital with the same ms, and this is called Huns Rule. This is actually Huns' first rule, but we'll just call it Huns Rule. So that's the second electron. The third electron in nitrogen is here. And now let's look at the electron affinity. Electron affinity is when an electron is added to the system. So this is nitrogen minus. When I add an electron, because of the Pauli exclusion principle, the next electron has to go down spin, so the 4 quantum numbers are different. And when I go in this direction, you see that we've had to add an electron to an orbital, an atomic orbital, which already has an electron, and that therefore will make it is that energetically favorable or unfavorable? And the answer is it's unfavorable, and therefore when we look at the electron affinity for nitrogen, it is a very small number, -7. By contrast, if I look at the ionization energy for nitrogen, then I am losing an electron, and there is no electron-electron repulsion term that can be considered, and so the ionization energy for nitrogen can be big. And there, the nitrogen has a big ionization energy due to imperfect shielding. Okay, let's consider one more case. We'll consider the case of boron. Boron is 1s2, 2s2, and we're again going to consider its electron affinity. Electron affinity is adding an electron. And when you add an electron in boron, it has to enter 2p. 2p is lower or higher in energy than 2s. It is higher in energy. And therefore, 2p, the electron affinity is, since it has to go to higher energy, the electron affinity is small or big. And the answer is, it's small because it has to go to higher energy. And sure enough, when you look up top, it's a negative number. It's switched on. It doesn't want to take the next electron. It's -19. Electron affinity is small. And this is called, this then is because we have to enter the next subshell. Subshell is the difference between 2s and 2p. Shell is the entire thing. We have to enter the next subshell, making, this is not supposed to be boron, this is supposed to be beryllium, sorry. Making beryllium's electron affinity small. And that's the effect for going to the next subshell. And the same thing is going to happen in even bigger terms when we have to go to the next shell. So the electron affinity For neon, where the next electron has to actually enter the third shell, is also going to be a small electron affinity, again, a small number. And so the deviations of ionization energy and electron affinity can be understood by electron interactions, the repulsion of electrons going to the same orbital as each other, and the fact that some shells are higher than other shells.